Okay, so the problem that we are going to discuss today is this. A neutral conducting sphere of radius r0 is placed in a previously uniform electric field of magnitude E0. Find a new perturbed electrostatic potential psi that satisfies the Laplace's equation. Okay, so I have a constant electric field of magnitude E0, and when I place a neutral conducting sphere in the electric field becomes modified. This new electric field we have to find by solving the Laplace equation with appropriate boundary conditions. So let us start the solution. So we select spherical polar coordinates with origin at the center of the conducting sphere. So at the center of this conducting sphere, it lies our origin of the coordinate system. And the z-axis is oriented parallel to the original uniform field. So the original uniform field was directed from the left towards the right. So that direction, we have taken it as the direction of the z-axis. And this choice will simplify the application of the boundary condition at the surface of the conductor. Okay. Now, to solve this Laplace equation, let us use the separation of variables technique. Okay. So separating variables, we note that because we require a solution to Laplace equation, the potential for r greater than r0 will be of the form psi r theta is equal to summation over L from 0 to infinity AL RL plus BL r to the power minus L minus 1 multiplied by PL cos theta. Okay. PL cos theta is our Legendre polynomial. Okay. In our earlier discussions, we use M instead of L, but here we are using L. Okay. So our solution will be independent of phi because of the axial symmetry of the problem. So here in this particular case, we have taken M equal to 0. So we have only the Legendre polynomials instead of the associated Legendre functions. Okay, so this is our solution to the Laplace equation, and we have to determine the values of AL and BL by using the boundary conditions. Okay. Okay. Because the insertion of the conducting sphere will have an effect that is local, the asymptotic behavior of psi must be of the form, that is, when r tends to infinity, psi must be of the form minus E0 times z. This was the value of the original field. Okay, I repeat, the insertion of the conducting sphere will have an effect that is local. The asymptotic behavior of psi must remain unchanged. That is, psi when r tends to infinity should be of this form. Okay, and z, we know from this, z is r cos theta. Say for example, okay, let me draw here. Let me draw any point. Okay. So take any point here, this point. Okay, and join it to the center of the coordinate system. This angle is theta. Okay, and what is the value of z? Z is, this part is the value of z. Okay, and z is this distance is r, so z is r cos theta. Very simple. Okay, z equal to r cos theta. So z is this distance. Okay, this is fine. Okay, so z is r cos theta, and cos theta is nothing but p1. Okay, so we call this equation number 2. Therefore, when you put r tends to infinity in equation number 1, in this equation number 1, when you insert r tends to infinity, this term vanishes. Okay, this term vanishes. What remains is only this term and this term. Okay, So when we put r tends to infinity, equation number 1 gives the left hand side is given by this expression, that is E0 r P1 cos theta, and this is equal to AL RL PL cos theta summation over L from 0 to infinity. Okay, this right hand side is given by this expression. This term goes to 0. What remains is only this term, and the left hand side is given by this expression. Okay, now comparing coefficients of PL cos theta on both sides, we get AL should be 0 for L greater than 1, because here on the left hand side, the only Legendre polynomial that we have here is P1. So that means all other PL for L greater than 0, sorry, L greater than 1 should be 0. So this P1 and this P1, if we compare it, what do we get? We get that A1 is equal to minus E0. So if we take L equal to 1, we get here A1 R P1 cos theta. And you compare with this E minus E0 R P1 cos theta. And so for the value L equal to 1, if you compare the left hand side and the right hand side, we find that A1 is equal to minus E0. Here we noted that if AL is not equal to 0 for any L greater than 1, then that term would dominate at large values of R, and the boundary condition, that is this particular condition given by equation number 2, could not be satisfied. Additionally, the neutrality of the conducting sphere requires that psi must not contain a contribution proportional to 1 by R. So we must also have B0 equal to 0. That is B0, V0. When L is equal to 0, this becomes R to the power minus 1. That means B0 by R. Okay, I repeat, when L is equal to 0, this term becomes B0 divided by R. Okay, and since the conducting sphere is neutral, psi must not contain a contribution proportional to 1 by R. So we must also have V0 equal to 0. That means as a second boundary condition, the conducting sphere must be an equipotential. That is, any conductor is an equipotential. The surface of any conductor is an equipotential surface, and not only that, the interior of the conductor, which is a solid conductor, is also an equipotential. That means all points on the conductor are at the same potential. Okay, and without loss of generality, we can set its potential to 0. Thus, on the sphere R equal to R0, that is on the sphere of radius R equal to R0, we will have, that is on the surface of the sphere, we will have this particular equation, that is psi. This is the potential on the surface of the sphere, and since the surface of the sphere is an equipotential surface, and we have set that potential on the surface to 0, we write psi equal to 0, and then we expand the right hand side. We expand the right hand side of this, where we have taken that AL is equal to 0 for L greater than 1. The only remaining terms, the only remaining coefficients of A are A1 and A0, and the remaining coefficients of B are from B2 to from B1, B2, and so on. So psi R0 theta is equal to 0. This is equal to A0 plus B1 by R0 square minus E0 R0 B1 by R0 square. We can get it from here. When you take R is equal to, L equal to 1, this will be B1 divided by R to the power minus 2, that is B1 by R square. And when you take R equal to R0, we get the expression B1 by R0 square. Okay. So we get this expression A0 plus B1 by R0 square minus E0 by E0 times R0. This is A1. This is here. We have this. A1 is E naught. Okay. So this is A1R, A1 times R from this expression. When L is equal to 1, we get A1 times R. And you put R equal to R naught, you get A1 R naught. And we already know that A1 is equal to minus E naught. So that is minus E naught R naught P1 cos theta plus L from 2 to infinity BL PL cos theta by R naught power L plus 1. This equation holds for all values of theta. This equation holds for all values of theta. This means coefficients of PL cos theta must vanish separately. Okay, that means all the coefficients of PL cos theta must vanish separately. Thus, A0 is equal to 0. This should also be equal to 0. That means B1 by R naught square is equal to E naught R naught. That means B1 is equal to E naught R naught cube. And then all these terms are 0. BL is equal to 0 for L greater than or equal to 2. So we substitute the value of A0, A1, B1, and so on to the expression. And what is the expression? To this expression, we substitute the values of A0, A1, B0, B1, and so on. Then we get the final expression like this. Psi r theta equal to E naught R P1 cos theta. Okay, this is A1 R P1 cos theta. Okay, and plus B1 by R square P1 cos theta. Okay, this is B1, this is A1. Okay, this is A1, this is B1. So from this, I take my minus E naught R P1 cos theta common. Then we get minus E naught R P1 cos theta, 1 minus R naught cube by R cube. And P1 cos theta is simply equal to cos theta. So we know that R cos theta is equal to Z. R cos theta is equal to Z. Therefore, we have psi is equal to minus E naught Z times 1 minus R0 cube by R cube. This is the final solution for the sphere placed in a uniform electric field. So let me pause the recording here.